Hi everybody! Today we are finally going to generalize the construction that we saw on our first session for elliptic curves. So that will be actually by defining the Jacobian of a curve of genus G. We will do that in two steps in a similar way as we did last session. First we will define it on like the more general side of things, and then we will consider the case over the complex numbers and see how that is much more tangible and explicit. So for section 1 we will talk about the Jacobian, and we will do so as an abelian variety associated to a curve C. So let me do first a small recap. Recall for a moment the construction that we saw for elliptic curves. And I will write it in a slightly weird way. So we have a curve E. To that we can associate the set of complex points of the curve, and this is what is isomorphic to a complex torus C modulo lambda. We have seen that this isomorphism here, it's due to the fact that the elliptic curve is actually an abelian variety. So basically this map, it's just like taking the set of points, but it's basically the identity. So the problem when we go to higher genus is that it's no longer true that the curve is an abelian variety. So the goal of this section is to introduce the abelian variety that will appear on this side of the diagram, that will be in turn isomorphic to the complex torus when considered over the complex numbers. Okay, so we will do that next. So with this idea in mind, take C to be a genus G curve, and let us define some groups that will be relevant. We define first the group deep of C, which is the set of divisors on the curve defined over the algebraic closure of the base field. We have div 0 of C, which is the set of degree 0 divisors on C over the algebraic closure of K, and prints of C the set of principal divisors. So for those that might not be fully familiar with divisors, it's just a formal sum of points. The degree, it's just the sum of the orders of at every point. And the principal divisors are divisors that come from looking at the zeros and poles of meromorphic functions. So with this setting, we define peak 0 of the curve as the degree 0 divisors quotient out by the principal divisors. And here is where our new abelian variety comes in. To a curve C, we associate in a natural way an abelian variety that we call the Jacobian of C. And denote as Jac of C. In general, I'll try to write it like this. Sometimes I will slip and write it as J of C. Just choose a notation and stick with it, or do your best. So we won't go into the details of how this abelian variety is naturally associated to the curve, but what we have is that it satisfies that the set of points of this abelian variety over the algebraic closure, it's equal to this Picard peak 0 of C. So in terms of divisors, we will denote call lambda C the natural polarization that we also get in this construction, and it will be principal. So let me give a bit something a bit more explicit. So we have that for a distinct point P in C over the algebraic closure, we define the Abel-Jacobi map with base point P as the morphism over K bar that is given as follows. We call it alpha, and it goes from the curve to the Jacobian over the algebraic closure, and it takes a point Q and maps it to the divisor Q minus P, where again P is this distinct point that we are choosing. And this choosing a point, it's actually consistent with what we did in the case of elliptic curves, where our distinctive point was just the point at infinity, or the the neutral element for the addition. So this is actually very analogous to what we saw. And this construction, we just extend it additively to divisors. So basically, if we take a divisor D, we just map it to D minus the degree of D times P, and it works all great. Note that the Jacobian of K bar, we said that it's the degree 0 divisors quotiented out by the principal divisors. So that should tell us that if we start with a divisor that is associated to a meromorphic function, its image should be 0. And this is actually what we will get in a moment through the Adel-Jacobi theorem. But first, as always, when we introduce an object, let me introduce the associated maps. So now, given two curves C prime with Jacobians, Jac of C prime, let phi be a morphism of curves. Then basically this morphism will induce homomorphisms in the different groups that we have defined associated to the curve, and this will in turn give us a morphism on the Jacobians in the end. So basically then it induces homomorphisms phi lower stars that goes from the divisors of C to the divisors of C prime by just taking a point, the class of a point, and mapping it to the class of its image by the morphism. And again, additively for divisors, we also have phi upper star, which goes from in the other directions, from the divisors of C prime to the divisors of C, and takes the class of a certain point Q and maps it to the sum for every point in the pre-image of Q of the order of the morphism at the point, where here we use a uniformizer around the point and everything, times the class of the point. The interesting thing about these two homomorphisms is that they map degree 0 divisors to degree 0 divisors and principal divisors to principal divisors, so we can actually consider them directly over pic 0. Let me write that. So in turn, Whoops, some water. So they induce homomorphisms that go on the peak zero of the curves. So phi lower star from peak zero of C to peak zero of C prime, and upper in the other direction. Okay, so as I was saying, we have these induced homomorphisms on the peak zero of C, and again, this is simply the Jacobian. It's a homomorphism in the points of the Jacobian, so it gives us the following commutative diagram. So here we will take again curve C prime related with a morphism. From C to its Jacobian we can go via the Abel Jacobi map alpha, and here we are taking the Abel Jacobi map alpha prime that is compatible with this morphism. We do that by taking the base point on the second curve to be the image by the morphism of the base point of the first curve, and then here we have that this is phi upper star with a lower star, sorry, as we have defined it before. So given a morphism on the side of curves, we have a morphism on the side of Jacobians, and the reverse is actually given by the following result, which is Torelli's theorem, which is very important for Jacobians. So Torelli's theorem let again C prime be curves of genus G, if their Jacobians are isomorphic as principally polarized abelian varieties, then C and C prime are also isomorphic. So two things about this result. The first one is that it's important that we are looking at the Jacobians as principally polarized abelian varieties. Remember that that gave us an extra condition that the isomorphism had to satisfy so that it was compatible with the polarizations. And second one, the result can actually be stated in a much more explicit way, where it actually tells us how the homomorphism, or the isomorphism in this case, on the Jacobian translates to an isomorphism on the curves. However, for sake of simplicity, we won't give that more precise statement here. I will reference it on the platform we are doing the course in. But yeah, so with this we have defined this abelian variety that we can associate to a curve C, and so now, as we have seen in every previous section, we can consider the case over the complex numbers, and in that case the Jacobian of the curve will be isomorphic to a complex torus. So what we will do in the following section is to construct a complex torus that we can associate to a curve, and then state the result that tells us that basically that's the complex torus that is isomorphic to the Jacobian of the curve. So that will be section 2, the Jacobian, a complex torus, associated to C. So the idea for this second part is to explicitly generalize the construction that we already saw in the first session for elliptic curves, which would be the dimension 1 case once more. So to a curve over the complex numbers, we associate first the space of holomorphic differential forms, which we will write as H super index 0 of omega sub C, the space of holomorphic differential forms. And this is a G-dimensional complex vector space. We will also associate the homology group of the curve over the integers. This corresponds, as we saw in the case of elliptic curves, to closed paths that are non-constrictable on the Riemann surface associated to the curve. And this is a free abelian group of rank 2G. And we can relate these two spaces by, in a very natural way, as follows. and we take from the first homology group, we go to the dual of the space of holomorphic differentials, and we do so by taking a path and mapping it to the morphism that takes a differential and computes the integral with the path. So this map is injective, and therefore it allows us to see the first homology group as a lattice inside the dual of the space of holomorphic differentials. So I hope that the next step is clear now. We have a g-dimensional complex vector space and a lattice of rank 2g inside of it. And this motivates the definition of the complex torus X given as this vector space quotient out by this lattice. So as before, now we can take bases on both spaces, and this will give us a period matrix. And in order to see that this complex torus is actually an abelian variety, we need to associate to it a Riemann form. So we will also see how to do that. Okay, now it looks better. So yeah, that's what we are going to do now, to describe X in terms of period matrices or matrices. Means to choose bases omega 1 omega g in H0 omega c. So we can take the bases in the space of holomorphic differentials and then just take the dual basis of that to be in the right space. Here I was missing dual. So yes, this map gives us this as the lattice and this, so the dual. Anyway, back to where I was. We can take the basis in the space of holomorphic differentials and then just take the dual basis of that to be in the right space. And we also take lambda 1, lambda 2g, an integer basis in the first homology group. And we obtain a period matrix that has entries in the integral over the path lambda j of the holomorphic differential omega I, omega not w, and this is just a g by 2g matrix with complex entries. And to this we associate one more matrix we define the matrix given by the oriented intersection pairing on the first homology group as follows. So in order to define this matrix, what we are going to say is what do we mean by saying that two paths intersect at a certain point, how to count them, and how that determines something for a given basis, determines a matrix for a given basis. So the intersection number of two paths alpha beta in the first homology group at a point P, which we denote by T sub index P of alpha beta, is, well, I'll just write it down here. We have three possible values for this. It can be 0, it can be 1, and it can be -1. It is 0 if the two paths don't intersect transversally. It's 1 if they intersect counterclockwise, and I will explain what I mean by that in a moment. And it's -1 if they intersect clockwise. So basically, when we look at a certain point at two paths, we have 4 different options. For example, this is alpha. If this is alpha and this is beta, at point P, the paths don't intersect. At point P, or the paths intersect tangentially. In that case, the intersection number is 0. And then we have the case alpha beta, beta alpha. And here is where the orientation comes in. We said that this is the oriented intersection pairing. So if we want to look at the intersection of alpha with beta, the order is important at a certain point P. We see that to go from alpha to beta, the turn is clockwise. So in this case, we have Tp of alpha beta equal to -1. Or in this case, we see that to go from alpha to beta, it's counterclockwise. So in this case, we have the intersection number equal to 1. So now we can define the intersection number of two paths. The intersection number of two paths, alpha, beta, it's just the sum for every point of the curve of the intersection number of alpha, beta at the point. And we define the matrix A that is given by entries T lambda I lambda j for ij between 1 and 2g. So the basis of the holomorphic differential that we have taken. The thing that is important about this matrix is that this is what we would take as the Riemann form for the complex torus that we have defined. And so I won't give the proof, but one can prove actually that the intersection matrix of the homology basis is the Riemann form by showing that it satisfies the Riemann conditions. So this would be a matter of going to the previous session, seeing the equations that we said that have to be satisfied in matricial form, and just seeing that it's satisfied for this example. I won't go into the details because this uses a whole lot of homology theory and Poincaré duality and other things, but if you're interested in the details or the topic, I will be sure to leave the reference on the platform so you can read about it. And so basically what this tells us is that this complex torus X that we have defined is actually an abelian variety. And I don't think that anyone will be surprised when I say that this is actually the Jacobian of the curve. To see that, we will actually see now an isomorphism between the two ways of looking at this abelian variety, the complex one that we defined explicitly and the other theoretical one that we defined in the previous section. So let me give that result now. So this theorem is due to Abel and Jacobi. Each of them prove one of the implications of what we are going to see now. So we have again that C is a curve with a distinct point P. Then the map H0 omega C dual quotient out by the homology that takes a point Q and maps it to taking W to the integral between P and Q of this. I think that this map will look familiar to you in the first session. It's the construction that we use to obtain the complex lattice associated to an elliptic curve. So we have that this map, let me give it a star so that we can reference it later, induces a canonical isomorphism between peak 0 of the curve and this complex torus. Which does not depend on the point P. So basically taking one point or another still gives us always an isomorphism. And the nice thing about this result, well, there are two things that I want to note. The first one is that when we identify the Jacobian of the curve with this complex torus, so they are isomorphic, but if we look at them as exactly the same thing, then this map that we have defined here is no other than the Abel-Jacobi map. That we defined in terms of divisors in the first section. This is the first point that I want to highlight. And the second point is that through this canonical isomorphism, we have actually that this theorem of Abel is nothing else than the generalization of the theorem of Abel that we saw for elliptic curves. Because remember that peak 0 of C, it's the degree 0 divisors quotient out by the principal divisors, which are the divisors that correspond to meromorphic functions. And if you remember, what we gave as the theorem of Abel in the elliptic curves case was that there existed a meromorphic function with a given expression for the zeros and poles, even only if some conditions on the divisor were satisfied. And those conditions are no other than that the divisor is principal. So that's exactly one of the implications of this theorem. Let me write it down. This theorem So ideally what we would want now is a similar result for dimension G in a very explicit way, so that we can again use theta functions to know things about the curve from the complex torus side of things. And that's exactly what we will do in the following section. And just to finish up with this one, I want to do again the standard choice that we are going to take for to represent the lattice of a Jacobian. So as we did for the general case of complex abelian varieties, we have that we can choose a symplectic basis of the homology, so that the intersection matrix is just the one that we wanted for such. In this case, we have the D is equal to the identity, because we know that the natural polarization that you can associate to a Jacobian is principal. So that just translates into a Riemann form that can be written on this shape. And actually, this is something that can be done very explicitly when we consider the Jacobian over C. So let me do this drawing. So this is the Riemann surface associated to a genus G curve. And in here we can just take some paths because we have a genus G curve. We have that it will be a torus with G handles, so G holes in the middle, as if you take a lot of donuts, bite into them and stick them together. We can take lambda 1 to lambda G to be the path that loops around one of the holes of the complex torus, and this is non-contractible precisely because we have this hole in the middle. And as the second part of this, the other G paths that we can take are the paths that go around the handle itself. This is just lambda G plus 1, lambda G plus 2, and this is just lambda 2G. And note that if you think of the definition that we saw for the intersection matrix, it is exactly this, because we have that lambda 1 only intersects with lambda G plus 1, and the way that they intersect is clockwise. Okay, there might be a sign on the wrong side. Through the magic of editing, we will add the note saying exactly where the signs go. Maybe it's just that I'm taking the wrong orientation for the paths, but as you can see, you can see that at least the intersection matrix for this choice of paths is exactly the one that gives me this matrix, except maybe for the sign. But the zeros and the ones in absolute value match with the definition that we gave. Yeah. Okay, so when we choose a symplectic basis of the homology on this form, we have that the Riemann form is of this shape. And so if we choose a basis of the holomorphic differentials such that the second half of the period matrix is just the identity, by just choosing the basis that corresponds to lambda G plus 1 lambda 2G. So let me write that. So we now take the basis of the holomorphic differential so that this integral, it's always given by it's either 1 or 0 according to the sub-indices. Then the big period matrix is simply pi equal omega identity of dimension G with omega in the single upper half space. And this is equivalent to the assumption that we did from a certain point onwards in the dimension 1 case, that we took lattices to be of the shape tau 1 with tau with imaginary part positive. And this we will do because the next step for the course is to give the generalization of the theta functions for higher dimensional abelian varieties.